Greetings from Fairbanks, Alaska. I'm Steffi Ickert-Bond, and I would first like to acknowledge my partners in crime, instructional designer Kristen Buffard and Associate Professor of Secondary Education, Dr. Uta Caden. Our talk is entitled North to the Future, Asynchronous Delivery of Systematic Botany at the University of Alaska Fairbanks. We have developed several asynchronous courses in biology and museum studies. Most importantly, Biology 195, Introduction to Alaska's Flora, is a 4-week asynchronous online course that was developed to provide equitable access to introductory science learning and has been offered since 2018. As the largest state in the Union, Alaska embodies 663,000 square miles, 1/3 of the territory of the U.S., of extraordinary scenic and wild country, the highest mountain on the continent, and extensive natural resources. Alaska has the lowest population density in the nation, with 1.3 people per mile squared. Approximately 32% live in rural areas and 17% live in communities with fewer than 2,500 people, the vast majority of whom live off the road or ferry system. Serving students in this vast rural area is a complex task, and online course delivery is a valuable alternative to on-campus enrollment for many of the rural students in our state. I teach a face-to-face systematic botany course in the spring semester, Biology 331, and I have always enjoyed the personal interaction with students. It was really important to me that the online teaching environment would simulate some of the interactions similar to having a student working on a microscope, where I can be looking over their shoulder. Designing online education using place-relevant pedagogy and the natural surroundings of where the students reside may increase curiosity and engagement in learning botany. One of the hallmarks of any systematic botany course is the hands-on learning experience in the lab. To create a similar lab experience for the online offering, we have carefully chosen technology that will allow students from all over the state, and even outside of Alaska, to collect data, perform plant dissections, and have a hands-on learning experience within the flora's native environment. We provide instructions for building a small plexiglass stand that can mimic a microscope by using a macro lens that attaches to your smartphone and allows plant dissection on the stage that can be moved up and down to provide focal length. Students don't just sit at their computers in this class. They go outside, touch with their hands, and share what they discover. They take detailed photos of flora on the go, with classifying metadata such as GPS location attached, and submission to iNaturalist to our project Plants and Fungi of Alaska. The technology not only lets students mimic lab spaces in their own natural areas, but also expands their digital networks, enabling them to share and collaborate with enthusiasts around the world and contribute citizen science data to research. This class makes use of citizen science platforms such as iNaturalists, and students contribute alongside other nature enthusiasts. The course design also includes carefully videotaped lectures using the Learning Glass platform. The Learning Glass collapses the perspectives of viewer and presenter into one shared perspective, providing an engaging learning environment. And no, I cannot draw backwards. I'll now show you an example of a Learning Glass video. Parallel with the leaf shape, and that is called parallel venation. So again, this is used to characterize and discuss what the leaves look like to help you identify what type of plant you have. There's a fourth kind of unusual type, and that's in gymnosperms. And that's in this very characteristic plant called ginkgo.
It's related to conifers, and it has dichotomous venation. So you have a dichotomy. They're branching in this type of fashion. It's very unusual and really only found in ginkgo. Parallel venation is often found in grasses. So that's a monocot. Corn, if you grow corn in your yard, you would have seen it, but all your grasses at your house would have this. And then the way the leaves are attached on the stem is leaf arrangement. And that again helps us to describe the plant. So we could have this type of arrangement, which is called alternate. So there's one leaf per node.
Many of you will have spent numerous hours in the lab with students looking through their eyepieces on the microscope and adjusted the field of view or made dissections for your students so that they can actually see some of the key structures mentioned in the keys you're using. It was important to me not to lose this personal aspect of the class, and I thought about how to best accommodate that in the online environment, and how to provide some guidance for plant dissections to the students. I've recorded detailed plant dissection videos for a number of the important plant families in Alaska. I'll show you an example of a dissection of Arabidopsis kamchatka using the Arctur video camera mounted on the top of my dissecting microscope. These videos are also very useful for my face-to-face class, Biology 331, as it is taught in the spring from January through May, a period when the interior of Alaska is under several feet of snow and little fresh plant material is available for dissection. The inflorescences of Arabidopsis kamchatka are racemes. They're few to several flowered, so each individual flower sits on its own pedicel. The four sepals are yellowish green, oblong to obovate, and often saccate at the base. The section where the four sepals have been removed, notice the 4 petals and the 6 stamens of differing length. There's 2 short stamens and 4 long stamens. This condition is called tetradynamous stamens. The petals in Arabidopsis kamchatka are clawed and generally between 5 and 6 millimeter in length, slightly shorter than the petals of the typical subspecies lyrata, which can get up to 8 millimeter in length. In this live dissection, I will show you how to remove the 6 stamens of Kamchatka rockcress. Note in the upper right-hand corner the clawed white petals, and in the lower left the yellowish saccate sepals of Kamchatka rockcress. So we have removed the 2 shorter stamens, and then notice the subsequent ones are longer in size. So there we have 3. This is the 4th stamen, another long one. So now we have 2 short and 2 long. There comes the 5th stamen. It's another long one. So 3 long and 2 short. This one is a little bit broken off, but it's still longer than the 2 short ones. And then finally the 6th stamen, which is another one of the 4 long ones. So we have 1, 2, 3, 4, 5, 6, and there's the ovary with the distal stigma and a very short style. In this dissected ovary and 3 stamens, we can see the terminal stigma and a very short, less than half a millimeter style. The fruits in Kamchatka rockcress are siliques. They sit on short, about 3 to 4 millimeter long pedicels. Here I show a dissected silique with the 2 outer valves and the central rhiplum where the seeds are attached. In this close-up view we can see the seed attachment to the rhiplum with the long funiculus. In this summary slide we can see the dissected flowers of Arabidopsis kamchatka with 4 yellowish sepals, 4 long clawed white petals, and the tetradynamis stamens, 4 long and 2 short stamens, a very short style, and the fruits that are siliques in Arabidopsis kamchatka. Remember those field trips from your systematic botany class when all students would get on the bus and drive to a new field trip location each Saturday? While it is fun to visit and explore each biome in person, it is not likely that you can get to all of them, especially in a place like Alaska. For our online systematic botany class, we've gathered 360-degree views of the different biomes in Alaska that you can use to explore and learn about each biome. It is like having your own private window looking into these amazing places, and you can use your computer to look around. A 360-degree camera was used to capture these biomes and give students a feel for some of the extraordinary scenic and wild country we have in Alaska. The class includes a number of interactive assignments that students post to the website and then comment on each other's work. They make observations in iNaturalist, press specimens and show images of their successes, and make plant dissections, documenting their dissections in ThingLink in a series of images, and I could watch their progress and give them feedback. It's basically just looking over their shoulders as they're working, like you would in a classroom environment. They use a plant bingo card to find plants in nature that feature these terms and post to the website. In our post-class survey, students commented on some of the elements that worked well and were most helpful. These included positive comments on some of the design elements, such as the learning glass lectures and the fact that students don't just sit at their computers in this class. They go outside, touch with their hands, and share what they discover in iNaturalist. It was exciting to see students take more control of their learning, as the instructor in the online format is no longer the key driver of the learning experience. This course is an exciting intersection of curiosity for wild plants, an exploration for Alaska's plant communities, and an accessible introduction to the science of botany. To highlight some additional learning aspects, we've also developed a plant ID card deck that students receive upon completion of the course. These include short write-ups of key characteristics, line drawings and photographs, and information about medicinal value. I hope this presentation has inspired you to give online delivery in your biology courses a try. I like to acknowledge some of the funding that allowed us to purchase special recording equipment for the development of these online courses. A special shout out to Don Pinkova, my PhD advisor, who was an intrepid botanist and inspiring educator. Please feel free to contact me if you have any questions about this presentation. Continue building your communities of citizen scientists and expand your networks and work together towards a better understanding of the flora of Alaska.